All right, so the last page in this packet, two population means independent samples. All right, this is much more straightforward because we're talking about means. All right, so I'm actually going to jump right to the type of test here. It's going to be a two-sample t-test. All right, we're testing a claim about two means. All right, and also it's not matched pairs. All right, so I figured I'd get that out of the way. All right, but we have Pete's Coffee's looking at two possible locations for a new shop. To help make a decision, they look at the number of pedestrians that go by each of the two locations in 1 hour segments. At the 5% significance level, test the claim that there is a significant difference in the number of pedestrians who go by each location. All right, so the question, significant difference in number of pedestrians. All right, assumptions, conditions. All right, so simple random sample. Assumption, they didn't say it, but what 1 hour segments are they referring to? In order for this to work, it would have to be selected at random. All right, normal distribution. Well, the sample size is at least 30. So n is greater than 30. Therefore, it's kind of weird. We're going to assume it's a normal distribution because we've met the condition that the sample size is greater than 30. They don't say anything about a population standard deviation. All right, now in the title it says that we're working with two independent samples, but then the question would be, are we really working with two independent samples? Right? And just bear in mind, on an assessment, they're not going to be labeled for you. No, this is a two population mean independent samples question. So you're going to have to let the assumptions conditions kind of drive which method you choose. All right, so looking at this, you have two different locations with two different groups of individuals. All right, so we are looking at two independent samples, but not because they told us. All right, it's because, I mean, and I don't know where these locations are, but you would assume that, oh, dangerous word. And it makes you want to throw it into the assumption category. But just play it out logically. They wouldn't be putting the coffee shop on the same street because then they would have access to the same foot traffic. They'd have to actually be in locations in which the foot traffic was, you had different types of foot traffic, right? Otherwise, why would they be assessing the differences between the two locations? All right, so the two independent samples is a logical conclusion from the structure of the problem. But it's hard not to use the word assume or assumption, even though, you know, it kind of is implied, but it's really more direct than that. All right, we're looking for a significant difference between the means. So the null is that the means are the same. The alternative, simple case of the means just not being the same. Test statistic. X bar 1 minus X bar 2 minus mu1 minus mu2 all over the square root of s1 squared over n1 plus s2 squared over n2. All right. 0.05 significance level, so we're going to get a 0.025 on either fringe. We need some critical values for our t's. All right, so the number of hours sampled, the smaller of the two entries here, is 35. So our degrees of freedom is going to be 34. So I'll just jot that in here. You know, it doesn't really matter where you put it. I'll put it here. All right, so you always choose the smaller of the two and reduce that value by 1. So inverse t, 0.025 with 34 degrees of freedom. And we're looking at negative 2.0322. With symmetry, we know that it's going to be a positive on the other side. All right, so for our test statistic, I'll just do that on the outside of the box. All the information is given to us, mean number of pedestrians, sample standard deviation, hours, all that good stuff. All right, so we can just pop it right in. 421 minus 347. I forgot everything else. 122 over 35, 122 squared over 35. And 85 squared over 50. All right, so just crunching some numbers. Go to my fraction tool. Get another fraction inside of a fraction. Fourth wall break inside of fourth wall break. That's like 16 walls. Movie reference? Anyone? Bonus credit? 1 point. Message me with that movie reference and I will award you said point. I mentioned, I think in the last video, that I'd be dropping Easter eggs in my videos to see if anybody's paying attention. So that was one of them. So you may want to, if you missed it, go back and rewind. You have the power of the internet now, so it's like, how hard could it be? You know. Anyway, hit enter and watch the magic. Okay, so 3.10. Well, if I round it to 3 significant, it's just going to be 3.100. All right, so definitely going to fall within the rejection area. So I want a TCDF. It's going to be on the high side, so 3.100 to something large. All right, also degrees of freedom. Always degrees of freedom. So I'll pop in like I usually do, like a 100. Oh, and like I always forget to do, let me store that in. All right, so we're going to get this number, the 0.001935 and so on. All right, so now let's run it through the calculator and I'll show you how this p-value that we're going to get is going to differ from this TCDF. So stat test, it was a 2-sample t-test. We did not use data, we used stats. Let me get my list of raw values here. Assuming it wants to let me type in, which for some reason it doesn't. Stat, 2-sample t-test, 421, 122, 35, 347, 85, and 50. This was a not equal situation, and we say no for pooled. All right, we're only going to work with non-pooled situations because we talked about this a couple of times, but basically it's the idea that you're not going to be able to assume that the populations are coming from distributions that are roughly the same. Right? So, and there's time and place for that, but that kind of makes it a little too, I don't want to say basic, but I also don't want to say, some convoluted explanation. It really kind of boils down to like what would be the purpose of this study to begin with if we already know the nature of the distribution. Right? So that's the one I'm going to go with. All right, so we got this point. I got my 3.100 and so on, but my p-value, if you do a quick comparison between that and the number that we came up with, so and go back to my home screen. I'll do this a couple of steps ago. Oh, you know what? I'll just retype it in. So it was vars, not vars, second vars, TCDF. I stored it in as A, if I'm not mistaken. Put a 100 in there with 34 degrees of freedom. So we got this number. Now, if I double it, it gives me that p-value, or at least something really, really close to it. All right. So the p-value is actually going to be for a two-tailed test. And this is annoying because it really doesn't have any understandable basis except to say that that's just the way it's done. The proper p-value would account for the percentage on both fringes. Right? So we'd have everything to the right of 3.1, but also to the left of negative 3.1. Right? The reason why they do that, and let me just write it down first, is logic based. 387. It's the idea that if you're going to have a not equal situation, you're looking at, this is the same as mu1 greater than mu2 or mu1 less than mu2. All right, so it's very by the book. So each one of these has a p-value of approximately 0.00194. All right. But p-value, you don't want to lose sight of the fact that p stands for probability, or the addition rule for probability tells us to add. So even though it wouldn't necessarily make sense to say it's greater than or less than, in that we wouldn't know one way or the other, because we could use a simple percentage to figure out which location seems to have more of a percentage than the other. The hypothesis test takes into account the fact that this is just one sample in infinitely many possible trials. And so it's basically saying that, in some instances, location A would have a higher percentage than B, and other instances, location B would have a higher percentage than A. And, when it all comes out in the wash, the percentage of instances in which they would be the same or different would associate itself with this p-value. All right, and so this p-value again gives us the probability of mistakenly rejecting that null, and that null is the default. All right, so if I'm going to reject that null hypothesis, I better have good enough reasons. So there's a lot in there to unpack, but that's really just it's really just rooted in probability, all right, as a lot of things are. All right, so it's a small p-value. We reject the null hypothesis. This conclusion should be a little bit easier to write than the last one. So there is sufficient evidence. Let me get it in closer. To reject the claim that the population mean number of pedestrians are the same, I'll say equal, at the two locations. At the 0.05 significance level. Therefore, the claim of a significant difference, or that there is a significant difference, is going to be false, is going to be true. I think I just randomly chose a truth value and I just said it. Yeah, so, it's kind of a wise ass answer though, because, if somebody asked you to conduct a study and determine whether there was a significant difference, I'm really debating where I should build my coffee shop. I got these two locations in mind. Can you just do a statistical analysis and let me know if there's a significant difference in foot traffic between these two places? And then, after a month or so, the person conducting the study comes back to you and says, I've conducted the study. I have conclusive evidence that there is a significant difference between the foot traffic at location A and location B. And then you say, cool. And then they reply, well, you didn't tell me to figure out which one's better. You're going to have to pay me to do another study. Now I got to do it again. And really, they just got to run another hypothesis test. But they didn't answer the question that you really wanted, but you weren't really specific in the way you asked the question to begin with. All right, so there's pros and cons to everything. But hopefully these tutorials have helped in some way. The next video series is going to be related to just confidence intervals, so it should go much quicker. But it's going to take the same format. It's going to have the flowcharts, the setup, and all that stuff. But it's also going to, like I said, be just more, let's crank out the numbers and draw a conclusion.